afternoon, everyone. Thank you for sticking with us. This is the last session of the day, and we will be covering why Google Kubernetes Engine is uniquely able and have the ability to support a reliability-first approach. My name is Kent Hua, and I am a Global Cloud Solution Manager with Google Cloud. And with me will be Fernando Hubo. He'll join us a little bit later. He is a Global Cloud Solution Architect with Google Cloud as well. So when we get started, as far as the agenda is concerned, the first topic we'll be looking into is how Kubernetes reliability, which is the topic of the day, and performance issues can be quite challenging to track. We'll also understand and look at how Google Cloud, in this case cloud monitoring, can help us visualize such potential hidden issues that are lurking within your environment, or if you're getting started, things to look for. Within the GK8 ecosystem is also how we can help balance reliability, performance, as well as cost efficiency, as they all play a role in us optimizing, but also understanding that reliability is a very critical element as part of the optimization process. So when we kind of talk about reliability and performance issues through this topic is last summer, we had released a white paper, the State of Kubernetes Cost Optimization Report, which covered a series of signals that organizations can evaluate to track, engage their optimization progress with these various signals. But one key thing we did find as part of this report was also that all of Kubernetes cost optimization, from what we see and what we actually analyzed and looked at through the report, based on varying type of clusters and how the ratios between them, was really understanding the importance of sending Kubernetes resource requests. So likelihood, most of us may be doing that. Some of times we may be overlooking it, but it's a very key factor because when we talk about sending resource requests inside our YAML files for the workloads that we deploy, it impacts a lot of things. Not only just the workload that we're deploying, but also for those of us that are familiar with Kubernetes, is the scheduling. Which node my particular workload will get deployed onto. That's all impacted by resource request. In addition to that is also bin packing. Bin packing, we all want to maximize that. From an operations perspective, maximize the resources that are available to me that are allocatable. So resource requests impact how bin packing is factored in. If I don't set resource requests, the node just thinks I have availability, or Kubernetes thinks I have availability within that particular node to schedule more workloads. And we'll walk through a scenario with that. Another component of Kubernetes that is impacted as a result of sending resource requests or requiring resource requests to be set are horizontal pod autoscaler. For us to scale out, Kubernetes needs to know how much my workload actually needs so that I can measure, and if I need to scale out more, based on my minimums and maximums within my horizontal pod autoscaler. The last component, which we're all talking about when we talk about optimization, potentially from the factor of scaling down, is cluster autoscaler. That one is critical as well. So if we look at a scenario where I don't set a resource request on my workload, I can schedule many, many of them, and my cluster will not scale up. It won't scale up until I hit some of my thresholds. First threshold that potentially could be hit would be my maximum number of pods that are available that can be scheduled within a node. Only then would it potentially schedule another node. So that's why sending resource requests can be very critical when I'm looking at deploying my workloads. But when we take about the Kubernetes aspect of it, and we think about the workloads and what we require based on SLOs, based on our business requirements, is the reliability factor. How much reliability do I need for my workload? Because that could determine whether or not I want to set requests. The performance. So I can set resource requests and the performance is impacted because potentially from a CPU perspective, I may be throttling my workloads at that point. I'm not telling the node or telling Kubernetes how much resources I actually need, and I can consume more, thus impacting my neighbors potentially within my workloads. As well as potentially, depending on the tools that you use, cost allocation. When looking at how much a workload potentially costs within a namespace for my particular line of business, resource requests for most tools use that mention of setting resource requests as the ability to track our cost allocation. And overall, as part of what we looked at in the State of Kubernetes Cost Optimization Report, is it's the baseline for cost optimization. Setting resource requests, all of these metrics are used throughout all reporting and constructs within what we see and visualize that we're able to either look for ourselves how we're doing or how we can communicate to our application teams on what resources are being committed. We'll take over a sample of that setting requests. So if we look at Kubernetes itself, 3 qualities of service for our workloads are available. The first one is best effort, not setting resource requests at all. I just deploy my workload and everything, it just goes. It gets deployed potentially, depending on what's available within my particular node. So in this particular case though, that pod can terminate at any given time based on the resources that are being consumed within that particular node or workloads that are being deployed in addition. The next quality of service is burstable, which is essentially I set my requests, potentially a little less, and maybe I allow it to use a little bit more by setting higher limits. In this particular case, my pods could be potentially terminated if I use more memory than what I request. But for the CPU case, as I mentioned, I can just keep throttling. I'll just use and throttle, use less resources. That could potentially impact the performance of my workload. And of course, the last one, if I match both my requests as well as my limits, I have a setting which is essentially guaranteed. Guaranteed in a sense as far as from a Kubernetes perspective, my workload wouldn't be torn down. Now I cannot control outside behaviors of a node going down. That's a different Kubernetes behavior that would need to be resolved, another node spinning up potentially. But the workload itself, as far as scheduled on that particular node and running, would not be impacted. So overall, within this, going back to the report, is for those workloads that are not setting resource requests, potentially increases the risk of intermittent, potentially hard to debug reliability issues. And we'll get into that a little bit deeper as far as how it can happen. But before I get to that is really kind of running through a scenario. If we take a node, this is a very sort of simplistic view, because if we can multiply by 1,000 for the amount of nodes or even more that could potentially be running in your particular cluster, is I have a single node, and that single node has used by regular pods resources. So if my single node has this capacity, which is the large rectangular box, that's so much capacity or allocatable resources that are being available, is I set a request of the blue. This is how much I'm asking for. Node, can you give it to me? Sure, it's about half used. But as far as requests are concerned, but actual consumption of utilization is about 40% probably. Variable numbers, but it's less, again, than the allocatable. And overall, we look at this for the next view is, there's still available resources. If I'm setting, think about this as memory requests in this particular case, asking for memory for within a particular node. So I can schedule more, sure. These are best effort pods. So remember, these aren't setting requests, or at least memory requests. And they're run, they're scheduling. Everything's happy, everything's great. So in the next scenario is, I'm gonna schedule more. I'm just gonna keep packing it in. I mentioned bin packing. Our bin packing numbers still only reflect the green and the blue. When we look at bin packing from a Kubernetes perspective, its perspective in Kubernetes when it schedules is that I only have blue and green. As far as I know, I can keep scheduling, in this case, yellow box or this top right-hand corner box from your perspective. Well, what happens is, if I keep scheduling or I exceed that threshold of what is actually allocatable, Kubernetes, it reaches into node pressure. If you saw that last quote that I had, when the node is under pressure, it needs to protect itself. And in order to protect itself, well, I probably have potentially some guaranteed resources as well as burstable workloads. But my best effort ones, well, unfortunately, 2 of these potential pods are going to be terminated as a result. Well, if it's terminated, well, everything's happy, right? Not necessarily. My workload may be available. I may have experienced disruption as part of my workload. I may have gone through this process, but I can go through this constant loop of my pods, tearing down, coming back up, tearing down, coming back up, which could potentially, we can exhibit bad behavior. Imagine our end user who's potentially looking at this. I'm running through my workloads and maybe I'm feeling it, maybe I'm not. But it may be impacting some of the numbers that we're using to monitor and observe the behavior of our particular cluster. So this is what happens if we don't set requests on some of our workloads. Scheduler will just keep packing away. So things may look great, but we'll look a little bit deeper a little bit later to see what else can potentially happen as a result of this. So if we look at just best effort, I'm not saying best effort is bad. Sometimes best effort does make sense. I've talked about reliability quite a bit in this couple of topics that I've had. The first question we ask with ourselves when we talk about best effort is, does my workload have a minimum level of reliability? That's one fact question. Yes or no? That's a question you can ask. If it doesn't, well, go ahead. Keep using best effort because it makes sense for your workload. The next one, batch jobs. Maybe batch jobs are a potential scenario. If I have batch jobs and I don't have a checkpoint, keyword being checkpoint. Remember those yellow boxes on the top right hand being terminated? If I'm not checkpointing, I'm going to have to restart my workload and I have to restart my potential job. So in this case, do my batch jobs recover and do I checkpoint? The next piece of it is, I mentioned about CPU throttling. Can I actually handle or function if my CPU gets throttled as a result of overloading my particular node? If the answer is yes, sure, best effort makes sense. So if we had said that best effort makes sense based on some of these questions, there's more things that we can do as a result when we took that from the factor of optimization. The first thing I can do is leverage Spot. So whether they're Spot pods or Spot nodes, these are preemptible. These are actually at a lower rate with the trade-off that these could be terminated at any given time. And because I checkpoint my batch workloads, I have no minimum level of reliability, I'm okay with CPU, well, go ahead, let's use Spot. And I can do that in one of two ways. The first way is I can actually set this node selector and say, true. And this is a GKA parameter that I can specify. In a more abstract parameter, I could potentially use node affinity, whether required scheduling or preferred during scheduling. So I can use node affinity to say, hey, I want to specify and I want to leverage Spot VMs or Spot nodes. That's another way for me to optimize, assuming that my workloads can take. If I can handle the scenario of what best effort does to my workload and how the Kubernetes cluster reacts, this is a potential scenario that I can leverage. Another is I can actually reduce the amount of time it takes for termination of my particular workload, graceful termination in this particular case, and I can set this, even though it's about 15 seconds, I can set it to lower. The lower the number I set, the quicker the workload is able to terminate. Thus, I no longer potentially need that workload running, potentially triggering further, because when I look at it from a single node, it's not as impactful. But if I'm looking at 1,000 nodes and I'm scaling down, it allows the cluster to react and potentially scale down as a result. So I can set this parameter, termination grace period, 15 seconds or less. Another factor that I can use if I am leveraging these best practices. Let's look at burstable in this particular scenario. So burstable is, remember if you recall, I set requests, but I set my limits a little bit higher because maybe I need to burst higher. Well, recall, if my memory is using more than one, in this case 100 megabytes of memory or megabits of memory, if I use more, there's potential that the cluster would say, hey, you're using a little bit more than you asked for, maybe we need to terminate you because someone else has a guaranteed resource that's being scheduled. So in this particular case, when we're using burstable, so what if your workload terminates due to a spike in memory consumption, as I just mentioned? Does this impact your end user experience? Because if it does impact our end user experience, we may not want to go this route. But if it doesn't, well, maybe it makes sense to have burstable. It gives our cluster a little flexibility in what resources are being made available to it. Back to the one that was best ever, which is related to batch jobs. Do our batch jobs need to run to completion? In this case, no checkpointing. Otherwise, if I don't checkpoint and my pod is terminated in this particular case, my job has to restart, which then is potentially additional resources, potentially wasted, time wasted. So with that, to be able to mitigate some of that is to look at that resource and setting guaranteed memory so that we mitigate our cluster from having to make that decision. We need these resources for our particular pod. So this again goes back to, do I need these particular workloads within my cluster? And I can set these different qualities of service. But with that, even though I say these particular settings, Why would it be so challenging? I just said it. If you set these parameters, everything will be great. So I'm going to have Fernando Hubo join us, and he's going to cover this.
Thank you, Kent. Can you hear me? Yes, I think so, because I can hear me. So the reason that the problem is challenging is that you may be having that problem in production, but you might not be seeing it. So here, the first example that's the challenging problem is that the problems happens in an intermittent manner, and they are hard to debug. So we don't know when the node is going to be full. We don't know when the node is going to be over pressure. So it can be today, tomorrow, 100 times today. So it's hard to predict. So when you look at your workloads, they will look something like this. They look all green. Sometimes they may be one red, but Kubernetes do its work, and then it gets green again. But the problem, the difference between a regular pod and a pod that was terminated abruptly is that a pod that was terminated abruptly received a Q -9. So it can be interrupt your transaction, it can interrupt your workload without graceful termination. So, but for Kubernetes, is basically, I don't have that pod. That pod doesn't exist, so it looks all green. The second reason is that Kubernetes out of the box don't have like observability tooling that's easy to track it, how many times it happened in the past. So I'm facing this problem. How many times I faced it in the past? Or what workloads are at risk? So this is a kind of challenging thing to be done. And the Kubernetes API, for example, when you deploy a new pod, if it's a best effort, it doesn't tell you, like, hey, do you know what you're doing? This is a best effort pod. It can be terminated at any moment. Basically, it deploys it, assuming that you understand what you're doing and that you understand the risk you are facing. Kubernetes also, as I mentioned before, it doesn't look backward. There is no tooling to look backwards and see what has happened or what workloads are at risk right now. And also, Kubernetes by itself doesn't provide recommendations. So in the research, we realized that the main opportunity for cost optimization is to right-size the workloads. So Kubernetes also don't provide it. The third, the last but not least reason why this is challenging is that the state of Kubernetes cost optimization we launched last year, it has shown, as Kent mentioned, 4 signals. It has presented us 4 signals. So the signals are the signals that we recommend everybody to track, that are the people that if you want to optimize your clusters. So the first signal, the workload right-sizing, is basically telling us, is the developer setting the request they are actually using? If the developer is setting 10 CPU for a pod, and they are using only 1, maybe we can save 9 CPUs in the scenario. So the second signal is basically, can I scale down at night? I don't have demand, so can I downscale my cluster? For that, it's a work that developers and platform admins need to work together, because developers need to scale down their workloads so that the cluster can follow. And the third one is bin packing. So am I using the entire CPU and memory from the cluster? Think about the node. You can use all the CPU and waste memory, or you can do the other way around, or you can not use either of those. So these are the resources signals, but there are also a discount signal. Because if you're running in the cloud, you can save by using, as Kent mentioned, Spot. Best effort should be running on Spot. Because if best effort can be terminated at any time, Spot gives you 15 seconds. Why are you paying more for that? So run best effort in Spot, and you're going to save money. If they are really best effort workloads, of course. Also, there are continuous use discounts. So if you are willing to pay less, you can commit to some time and get some discounts. But what I want to show you is how these signals can be impacted if you use best effort workloads. And let me drive you through some scenarios. First, I'm going to show about the workload right-sizing. So what are the situation and how best effort workloads impact workload right-sizing? So as you can see, workload right-sizing is basically a matter of checking what are the used resources comparing to what have been requested. So if you look at this, as Kent mentioned before, this is a cluster of a single node, just for simplicity, and this is the memory being requested. These are the pods being deployed with the memory being requested. And these are the actual memory being used. So in this scenario, what the workload right-sizing is telling me is that in a cluster level or in a node level, I have 50%, or using 50% what I'm being requested. The point here is that we need to pay attention is that best effort pods can change this metric. And it can change for good, and it can change for bad. I'll explain shortly why. If I know exactly those pods are a really best effort, I don't care if they receive a Q minus 9 right now, or any time in the future, or 100 times in a single minute, that's super good to use them, because they are using the space that you were not using before, so they are saving you money. And that ends up that our new metric that's resources used is basically all these things versus requested resources, the blue one. We are using 9% what you have requested. So it's a good point. The challenge is when we don't understand what are running in the best effort. What are running in the best effort workloads? Are they really best effort? Can they receive a Q minus 9 right now? If they are not, they cannot, like this number is basically inflated. Oh, sorry. This number is basically inflated. The reason is, well, developers are actually requesting this and using this. And then for them, it need to look like they are using 90% what they have requested. So the number can be skewed if we don't know what are running here. So the takeaway from this slide is basically you need to figure out each workload that's best effort workload that's running your cluster and figure out if they are really best effort, if they can be receiving a Q minus 9. So the second metric that can be skewed is the bin packing. So and this bin packing is not only a case of giving a possible inaccurate number, but it's also think like that. This is our cluster allocatable resources. This is our bin packing, 50%. So we have requested 50% of the cluster. That's fine. I am, as a platform admin, I can look, okay, I have all these empty thing, nobody's using it, so it's idle. Why am I paying for it? As a platform admin, I can decide to cut here, like there are many strategies for doing that. I can scale down faster, I can, using optimized utilization profile, I can force a scale down, I can change machine shapes to have less memory. So there are numerous strategies for platform admin to do in this scenario. The problem is, if I see the platform admin cuts, like the node size for at this point, what happens is that we have lots of best effort pods that nobody's seeing. So this will gonna happen is they're gonna be in looping, killing each other, and it's gonna be like lots of problems in this cluster. And by the way, cluster outscaler will not be triggered because cluster outscaler look at the resources request. So in this single node case, even that I have hundreds of pods, hundreds of pods here, cluster outscaler not going to be triggered to create a new node. So the takeaway here is that if you have this scenario that you have lots of best effort pods and you don't know if they are really best effort, you should not pack your cluster. So the more you pack, the bigger is your problem. And I'll tell a story that happened with me one and a half years ago where the customer came to me, the CTO came to me and said, Okay, I was running on VMs, and I have no problems at all. Then people told me Kubernetes was cheaper to run. I decided to move all my workloads, my entire company to Kubernetes, and then I started to see problems all around. And we had to over-provision by 3 times. So today I pay close to 3 times what I was paying on VMs. And with a quick analysis, we have seen they had around 70% of their workloads not setting requests. And that's not uncommon. 50%, there are lots of people that have that. So the point is, their workloads were very unstable, and they keep adding more VMs, bigger VMs, so that they can stabilize their workloads. But they didn't eliminate the problem, because one node can still get full and can be killing pods. So this is a common use case, and then we have seen this pattern in the research. So the cluster that have the most number of best effort workloads are the most over-provisioned ones. Okay, because people see the problem, and instead of going to the root cause, they add harder to the problem. They mitigate the problem, but they don't eliminate it. So right now, the reliability approach is basically, it's very simple. It's a matter of us to looking at those workloads before trying to your cost optimization journey. Because if you start your cost optimization journey, your platform admins you want to pack the clusters because they are receiving pressure from the CTO or CEO or the CFO, and they're gonna be starting to have some reliability issues. So there are two kinds of pods you need to pay attention. The pods that don't set requests, mainly on memory, because memory, there is no way to compact memory. So what kubelet does, it kills the pod. And pods that are under-provisioned on CPU, under-provisioned on memory. Those pods have the same problem that best effort workloads. So you need to figure out those scenarios. You need to talk to your developer teams, and you need to figure out if they are really supposed to be this way. Then you can start your journey with cost optimization once you figure that out. And you just need to remember that cost optimization is basically a continuous discipline. So it's not done once and it's all done. There are good ways to do that. You can create guardrails. You can improve your pipeline, your CI/CD pipeline, so that you can catch those problems early in the cycle, in the process. So, and why GKE is uniquely positioned to support this reliability first approach? GKE allows us to identify workloads that were abruptly terminated in the past. So we don't need to try to monitor right now what has happened. There is a way to look at the cloud monitoring and find what has happened in the past. I have a demo to show you here. And this is my project, pet project. I'm looking at the workloads. And as you can see, there is no problem with my workloads. I don't have too many. It's just a few. It's just a pet project for my experiment. And even if I refresh it, there is no problem. So sometimes, as I mentioned, can have a problem, but when you like Kubernetes will create a new pod for you. If you go to logging and Log Explorer, what we can do is to run a query that will tell us, because cloud monitoring stores your 30 days of logging. So this query basically are looking all the points that can be killing the pod abruptly. And as you can see here, in just 14 days, I have close to 8K pods, or 8,000 pods being killed abruptly. So the way we look at it, we look at the kubelet. So is the kubelet catching this problem? If the kubelet is catching this problem, we have a little bit more information. But sometimes it's not the kubelet, it's a containerd that's catching this problem. So kubelet don't even realize the problem has happened. And sometimes it's the node, the kernel of the node. that gets the problem. So containerd and kubelet don't even realize the problem has happened. So here, as you can see, I'm using the Gemini Cloud Assist to just simplify our life. But here we can see when kubelet catch the problem, we can see exactly what pod was killed and why, was terminated abruptly. When we look at, for example, one case that are for the containerd or the container runtime, we can see that the information starts to not be that as good as before because we don't know exactly which pod is anymore. We know what's the pod ID. So to debug this, we need to go into the container runtime and figure out what was the pod for that ID. In the third case, when the kernel catches it, you're going to be seeing that also using Cloud Assist, you're going to be seeing that it's even harder because the kernel is going to say, I killed a process. So what process was that? It's a number. So it's very difficult to track these scenarios. So that's why it's challenging. Tracking, figuring out what has happened. We now can see how many times it has happened, but we cannot tell exactly where the problem is. So we can tell when kubelet kills it, but not when the container runtime and the kernel. So the second reason that GKE helps us to figure out is that we can figure out what workloads are at risk. So in the early demo, we have run a query to figure out the workloads in the past that have been killed abruptly. And right now we want to understand what are workloads that I have deployed that are at risk of being abruptly terminated in the future. And if you go, I will wait a little bit, you can take a picture of this if you will. We have the QR code here and also the link up there. This link will go open a dashboard for you with exactly this information. It will tell you how much of your workloads are being not setting requests, or how many of your workloads are under provisional memory. And it's also gonna prioritize for you with which workload you should focus first, because it will order by the ones that are wasting the most. And if you scroll later down these, it will give you some recommendations. They are not the best recommendation because we pick a small window for this one, but it gives you some recommendation, at least serves as a quick start. If you're doing more in-depth optimization, we recommend to go with this link, also this QR code. This is a tutorial, but it has a Terraform script for you to deploy this tutorial. What this does is basically provide the same information as before, also provide you the priority, what you should be optimizing first. And the best thing I like from this dashboard is that you can customize as you will. You can create alerts, if you will. You can do whatever. The data is yours. We put the data in BigQuery, and you can do whatever you want in that. And the other thing is that we can track over time. So if you had 1,000 pods not setting requests when we start the journey, how many pods do we have right now? So we can track what's happening. Or we can track also what are how are doing my optimization thing. Am I saving resources? Because in the past I was using 1 million CPU. Right now I'm using 700. So I'm running more workloads with less CPUs, for example. And also it provides recommendations for your workloads. They pick like an interval of 30 days. So that's more consistent. And how we recommend is explained in the paper, or we build the recommendations. The other thing is that if you remember, I presented you the golden signals. So this dashboard helps you to visualize the golden signal over time. So if you're getting better or not. This is a good summary for the C-level. So the C-level you can present like how you're doing on your CPU, on your right sizing, on your bin packing, and if you're able to scale down at night or at any low demand period. GKE also provide a lot of features built in, and also we have many partners that you can use to help you in this process. So on the GKE side, we have one video that was done by our friend Anthony Bouchon that gives you a summary. What are the options that you have into GKE to realize how you are doing? So if you haven't never seen, probably already, but they have cost optimization tab, helps you to see if you are scaling down or not, how right-sized are your workloads, if they are best effort or not, but there are many other features that Anthony goes through. If you are a customer of GKE Enterprise, we also have a bundle in the policy controller that gives you all the best practices. It's just a matter of enable a checkbox. So if you are a customer of GKE Enterprise, I recommend you to go there and enable this bundle, the reliability and cost optimization bundle. So this will help you to analyze what workloads are already, what workloads have which problem based on the best practice. One thing that I would recommend you is that don't enable all them for to guardrails to avoid being deployed your pods on the cluster until you're sure what you're doing. Because otherwise, many of your pods can be blocked for being deployed. And if you do that, enable one best practice per time. Otherwise, if you have 100,000 workloads, you may be breaking some if you do that all at once. This morning also we have presented more things on the fleet on GKE for GKE Enterprise. So we are adding features that we're going to be helping you to understand your costs. There are features that you're going to be recommending the best practices. There are features that you're going to be showing you what are the pods that are best effort workloads. So there are many features that are coming in the short future. So with that, I would like you to provide your feedback, and we are open for Q&A.